Hey there, today we're going to talk about chemical equations, starting off with a look at how to read and interpret them. So, a chemical equation is a symbolic description of a chemical reaction. It shows the identities and the relative amounts of the substances that are involved. And so one example of this is in the process of coal gasification, carbon in the coal reacts with oxygen and water to form hydrogen and carbon monoxide. That would be a verbal description of the reaction. And if we wanted to express this symbolically, we could write it as 3 carbons plus oxygen plus water reacts to produce hydrogen and 3 carbon monoxide. So in this description of the chemical reaction, we have substances that are reacting on the left side. These are called reactants. And substances that are being produced are on the right side. These are the products. And then another thing to notice is that there are different amounts of the various substances. There's 3 times as much carbon as there is oxygen and water on the left. There's 3 times as much carbon monoxide as there is hydrogen on the right. And these multipliers are called the coefficients of the substances, and they indicate the relative amounts of reactant and product that are participating in the reaction. Substances that don't have a written coefficient are understood to have a coefficient of 1. Something like this kind of description is called a chemical equation, even though it's not usually written with an equal sign. You can write it with an equal sign, but more commonly you'll see these written with an arrow going from the reactants to the products. And as I said before, coefficients of 1 are usually left out. So it's understood that in this reaction there are 3 carbons, there's 1 oxygen, there's 1 water, there's 1 hydrogen molecule, and there are 3 carbon monoxide molecules. Now, one way that we can understand a chemical equation like this is we can think of it to represent individual atoms and molecules that are reacting. So in this example, we could imagine 3 carbon atoms reacting with 1 oxygen molecule and 1 water molecule to form a molecule of hydrogen and 3 molecules of carbon monoxide. That's a perfectly valid way to understand what this chemical equation is describing. But more commonly, when we write chemical equations like this, we're talking about reactions involving bulk amounts of the reactants and products. So not just a single set of atoms and molecules, but instead, for instance, in this case, we might have 3 moles of carbon reacting with 1 mole of oxygen, 1 mole of water to form 1 mole of hydrogen and 3 moles of carbon monoxide. And another thing that's important is that the coefficients in a chemical equation are representing relative amounts. And so we don't have to have exactly 3 moles of carbon, 1 mole of oxygen, 1 mole of water reacting to form 1 mole of hydrogen and 3 moles of carbon monoxide. What the chemical equation is telling us is that whatever the amount of oxygen and water that are reacting, 3 times as much of the carbon is reacting. And so if we had n moles of oxygen and n moles of water, they would react with 3n moles of carbon, and they'd be forming n moles of hydrogen and 3n moles of carbon monoxide. So these chemical equations generally are representing bulk amounts of the reacting substances, and again, these coefficients represent the relative quantities of the reactants and products that are in the reaction. So the next thing I want to talk a little bit about is what we mean by balanced chemical equations. So far the reaction equation that I've talked to you about has been a balanced chemical equation. And in such an equation, there are equal amounts of each element on the reactant side and on the product side. So again, in our reaction here, if you look at the left side of the equation on the reactants, there are 3 carbons. On the right, on the product side, there are also 3 carbons. On the left, we've got 2 oxygen atoms in O2 and 1 oxygen atom in water. And then there are 3 oxygen atoms altogether on the right, on the product side. And so the oxygens are balanced. And then likewise for the hydrogen, we have a total of 2 hydrogen atoms on the left, on the reactant side, and 2 hydrogen atoms on the right, on the product side. And so this chemical equation could be said to be balanced. You can certainly write a chemical equation that is not balanced, and then you would have unequal amounts on each side. So one easy example of that would be if we just took the same chemical reaction and left out the coefficients. So if we had just carbon plus oxygen plus water goes to form hydrogen and carbon monoxide, this would also describe the process of coal gasification, but it doesn't show us the relative amounts of the different substances that are reacting. So again, an equation like this isn't wrong. It still describes the same process. It describes the substances that are in the reaction. It just doesn't describe the relative amounts of the substances. And since it doesn't give us that information, the unbalanced chemical equation is generally less useful than the balanced chemical equation. And normally, if when we're working with chemical equations, we do like to balance them, because by having a balanced chemical equation, it does give us extra information. It tells us about the relative amounts of the reactants and the products. And in a future video, we'll talk about how we would go about balancing an equation that is initially unbalanced. Another thing I want to say about the coefficients in a chemical equation is that it's common practice to use the smallest possible whole number coefficients when you're writing a chemical equation. And so the example that we've been talking about does have the smallest possible whole number coefficients. We've got 1 oxygen and water, 1 hydrogen. We've got 3 carbons and 3 carbon monoxides. And this would be the standard way of writing this reaction. But we don't have to have our coefficients in the smallest possible whole number values. We can change those coefficients as long as the relative amounts of the reactants and products are the same. The numbers themselves don't really matter. So you don't have to use the smallest possible whole number coefficients. For example, we could double all the coefficients in this reaction. We could have 6 carbons plus 2 oxygens plus 2 waters, give us 2 hydrogen molecules and 2 carbon monoxide molecules. That's a perfectly valid description of this chemical reaction. It's not the smallest possible set of coefficients, but it's perfectly good. Likewise, the coefficients don't have to be whole numbers. If you take the original reaction and divide all the coefficients by 3, that would give us carbon plus 1/3 oxygen plus 1/3 water, gives us 1/3 hydrogen and 1 carbon monoxide. And this doesn't seem like it makes sense if we're thinking of individual atoms and molecules. It's hard to imagine how you could have 1/3 of an oxygen molecule, for example. But if we think of the chemical equation as reacting, as representing bulk substances, what this is telling us is that we've got whatever the amount of carbon is that's reacting, 1/3 of that amount of oxygen is reacting, 1/3 of the carbon amount of water is reacting. And so this, again, is a perfectly good description of a chemical equation. And you might well want to write this reaction in this way. For instance, if you wanted to emphasize what happens to carbon in the process of coal gasification, we might want to emphasize the fact that the amounts of oxygen and water are 1/3 of the amount of carbon. So this is perfectly fine, although it is non-standard. And you can get even crazier. If you wanted to, you could say 12/17 carbon plus 4/17 oxygen plus 4/17 water gives 4/17 hydrogen plus 12/17 carbon monoxide. This is still a correct description of the chemical reaction. The relative amounts of carbon and oxygen, for instance, are still 3 to 1. It's a little harder to see why you'd want to write the reaction this way. So, I kind of raise my eyebrow at this set of coefficients, but it's not wrong. It's just it's hard to see why you'd want to do it this way. So there is more. There is other information that can be included in a chemical equation, and this is all part of thinking of a chemical equation as describing a chemical reaction. So we've already seen how a chemical equation can describe what the substances are that are in a chemical reaction, and it can describe how much of those substances, the relative amounts of the substances. We can also describe the form of the substances. So the physical states of reactants and products can also be included. They don't have to be, but they often are, and it's kind of nice to have that information in the equation. Here's an example of this. This is sodium bicarbonate reacting with hydrochloric acid to form sodium chloride, water, and carbon dioxide. And here, after each of the formulas for the reactants and products, we've added a little label for the state of matter that each of them is in. So the sodium bicarbonate, NaHCO3, is a solid. We can represent that using the letter S in parentheses after the formula. The hydrochloric acid here is an aqueous solution. That is to say, it's dissolved in water. And we can represent that by writing the abbreviation AQ in parentheses after the formula. On the product side, the sodium chloride would be another aqueous solution in this particular reaction. The water is in the liquid state, so we'd write that as, well, with the abbreviation L. And carbon dioxide is a gas. We can represent that with the letter G. There are other phase labels that are used, but these four are the common ones that you're going to be encountering over and over again. Another piece of information that is sometimes included when you write a chemical equation is sometimes if you want to emphasize special conditions for a reaction, you can label those conditions on the arrow. Probably the most common example of that is shown here, where 2 moles of sodium bicarbonate are heated to decompose into sodium carbonate plus water vapor and carbon dioxide gas. And if we want to emphasize that this reaction takes place under heating, we can write a little triangle over the arrow. The triangle is actually derived from an old alchemical symbol. Triangle used to be used to represent the classical element of fire, as in earth, air, water, and fire. Triangle was used because it sort of looks like a flame. And so if you want to show that a reaction is taking place under heating, one way that you can do that is you can put a little triangle over the arrow, and that tells the reader that this reaction is taking place while it's being heated. You certainly don't have to include the little triangle there, but it does give a little bit of information. Another example of extra information that you can write on a reaction arrow is the reaction for the Haber process, where nitrogen gas combines with hydrogen gas in the presence of a catalyst and a high temperature and pressure to form ammonia. If we wanted to emphasize the conditions for this reaction, the catalyst, in this case a mixture of iron and molybdenum, the high temperature, 723 kelvins, high pressure, 200 atmospheres, we could write those on the reaction arrow. And that's just another example of extra information that can be written into a chemical equation. That's it for this part of our discussion. We'll talk a little bit more about chemical equations in the next video.